Greetings, physicists! This video will be about how to solve problems involving rotational motion and also some rotational kinetic energy. So, we got a car, your car apparently, you're going highway speed, and they were generous enough to calculate that in meters per second for us. And we know how big your tires are, and we are curious about how many times per second your tires rotate, and also the speed at the top of the tire relative to the ground. Alright. Well, let's draw a tire here. All four of them should be pretty much the same, assuming you don't put mismatched tires on your car. We'll assume they are going with a velocity in this direction. And for a rolling object, we can say that the center of the tire, as well as any point on the outside edge that's along that horizontal line that I just drew, should have a velocity, should have an angular velocity defined by this equation, v equals r omega. Now that's at the front point of the tire and at the back point of the tire. It changes at every other point, but typically you're not going to be asked for a point here. You could either be asked for this line here, you could ask for the top or the bottom, because those are for this level of physics, that's easy enough. Alright, how many times per second does each tire rotate? Times per second, well that's like revolutions per second, that's an omega. So we are looking for omega. So if we resolve this, we will get v over r. And we have both of those. A linear velocity was given to us, and a radius was given to us. So let's plug those in. We have a linear velocity of 29 meters over seconds, divided by a radius 0.30 meters. And because that radius is also 1 radian, we will get our answer in radians per second. That's how this works. So, let's plug this in the old calculator. We are going to get 29 divided by 0.3. Did that do it? 29 divided by 0.3. There we go. 96.66666. Okay, so 97. And this is a 2 sig fig problem, so we're going to get 97 radians per second. Or 97 times per second. Ooh. Excuse me, that's radians per second, and we need to put that in terms of revolutions per second, because one time the tire rotates is not 1 radian. It's 2 pi radians. So, to put this in terms of revolutions, we will make the following. This now becomes a stoichiometry problem. It becomes a dimensional analysis problem. So we are going to say that 1 revolution equals 2 pi radians. And what we want is revolutions per second. So let's do the 97. 97 radians per second times, we want to get rid of radians, we want to get revolutions. And I know 1 revolution is worth 2 pi radians. So I have to take my answer, divide by 2 pi. So divide by 2, divide by pi, and that's a lot less. So that's 15, if I round it, 15 revolutions per second. That's pretty quick, think about it. That means on the freeway, assuming you have 3/10 of a meter diameter tires. Radius tires? Radius, good. Otherwise I did this wrong. Yeah, if you have 0.3 meter radius tires, they spin 15 times every second. They're really clipping along. Okay, now, second question. What is the speed of the point at the top of the tire? That's this point here. Well, remember, in a rolling object that rolls without slipping, the bottom point down here has a v equal to 0. The middle point here had a v equal to r omega, and the top point here was going to be going twice as fast as the midpoint, or 2r omega. So we just basically have to double this. So if the middle point is going 30, then the top point up here is going to, the midpoint is going 15. Did it in my head too fast. The top point will go 30 meters per second. And it said speed relative to the ground, so they are talking about a linear speed, not an angular speed. The angular speed is still 15 revolutions per second. And I just messed that up, didn't I? Because, if you look, I doubled 15 revolutions per second when I should be doubling the linear speed, which was 29 meters per second. So you're getting to see me make a lot of mistakes today. So the speed at the top is just double the linear speed, and if you double 29, you're going to get 58 meters per second. Not too bad. Okay. On we go. We have a gyroscope. Remember those toys? It's like a spinning axle, and it's got a big ring around it. Sometimes they have multiple rings, but you wind it up and you let it go. Alright. And they're axle free to turn on bearings, meaning they don't have any friction, is what they mean by that. And to get it spinning, you wind a rope around it, around the center, and you pull it real fast. It's wound around the axle itself, so that this spinning axle here that you wind the rope around or the string around is very small, 2 millimeters. And you pull it with 5 newtons of force. And they tell us the diameter of the whole ring, so the ring itself, outside of the axle, has a 5 centimeter diameter. And the axle only has a 2 millimeter diameter. Okay. And we know its whole mass is 30 grams, which I'm going to go ahead and put in kilos, which is 0.03 kilos. I should probably do that with my millimeters and centimeters. This is 0.002 meters. This is 0.05 meters. Just to get all my units proper. And we want to know the rate it spins in RPM, revolutions per minute, once the string is completely unwound. So there'll be some stoichiometry in this problem too. So a lot going on here. Alright, what can we do with this gyroscope? It looks like a torque problem here. So if I tilt this on the side, if I look at it from the top, for instance, I have that little diameter there, and I have the big diameter of the ring up here, and the string where the force is being applied here. So really the force is being applied and causing a torque based on the diameter, the 2 millimeter diameter, if you can picture that. And because it attaches right there at the edge, that there will always be 90 degrees. So the torque here is equal to R cross F, but we're not going to need a sine or cosine anything because they are orthogonal to each other. And that torque should cause an angular acceleration. So let's think what we have. We have, let's see here. The ring's diameter is, oh, that's not what I want. A 30 centimeter long string. That's kind of important. So essentially, I start pulling here, and then I pull all the way out to here until the string is completely unwound. And that's 30 centimeters of string, or 0.30 meters of string that I've pulled out. Well, where was that string wound around? It was wound around this circle here. And if that string doesn't slip around that axle, then when I pull it 30 centimeters, then imagine this point right here on that surface, that point has also gone around that circle a total distance of 30 centimeters. The axle itself has rotated through an angular distance of 30 centimeters. So that's also interesting, or 0.3 meters. So we can put that in here. We would need to think of that in terms of radians. So for a circle that's 0.2 millimeters, or sorry, 2 millimeters, so 0.002 meters, has run out, that's 0.002 meters is going to be equal to 1 radian for this little circle here. So if I pull it out a total of 0.3 meters, well, that's 0.3 meters times, we know 1 radian is the same as 0.002 meters. And I could then figure out how many radians that circle has rotated. So what I'm doing is I'm changing a linear distance into an angular distance. That's going to be like 300 divided by 2, I think. Yeah. So I'm going to get 150 radians, and that's a delta theta. So I'm taking a linear distance and turning it into an angular distance, and we ought to be able to do that. Okay, so I have a theta. That's a given, that's 150. I have, what else do I have? I've got mass, that's fine. Let's go up here. I have, I'm going to go ahead and say I have a starting velocity. We're going to say it starts at rest. So V naught and omega naught are both going to be equal to 0. So whether I need linear or whether I need angular, I've got it covered. So I've got theta, I've got omega, and with this equation here, I should be able to get an acceleration. So let's make that equation happen. So if we have a torque, which we do, the torque will cause an I alpha. Alright, so we will need, I think we have the force in newtons, we have the radius at which the torque is being applied, and we're just going to need an angular, or a moment of inertia. Now, the trickiness here, the torque is being applied at this point, but the object that's moving is the whole, I mean, there are spokes here and stuff, so it's the center axle plus the giant hoop here. So let's make sure I have those. I think, this is my intuition based on this problem, they give us the diameter of the ring is 50 centimeters, or 5 centimeters, and they give us its mass is 30 grams. And I'm assuming then that the axle is very light, comparatively speaking. Otherwise, I don't think there's a way to solve this, because what you would really do here is you would take the moment of inertia of the axle and the moment of inertia of the ring together, because they're all spinning as one big piece, and you would say that is the total moment of inertia of the entire gyroscope. But if you'll notice, they only give us the mass of the ring. I don't think they give us the mass of the axle itself. So I have to assume that means that we're claiming the axle is not a significant mass compared to the mass of the total ring. And I'll make that point up here too. A heavy ring connected by light spokes. So they don't want you to think of the spokes and the axle as contributing much to the moment of inertia, which the axle wouldn't anyway, because its radius is so small. So its mr squared is going to be also very small compared to the ring. So we're going to say that the axle and the spokes are a very small percentage of the total moment of inertia. So I'm really going to use the 5 centimeters and the 30 grams. Whew. Lot in this problem. All right, so the moment of inertia for a hoop, right? The axle is one big hoop, a thin hoop, we'll say. We'll call it mr squared. And for this guy, well, let's see if I can combine all this stuff before I start plugging things in, because ideally that's what I should be doing anyway. So the torque then, the torque will be equal to mr squared times alpha. But the torque is also r cross f, so I have r cross f, which I know both of those things is going to be equal to mr squared alpha. And the alpha here, now we need an alpha equation. And again, I have alpha, I have omega naught, and theta, and I'm looking for omega final. I think then that the equation that I'm going to wind up choosing is this one, that omega squared equal omega naught squared plus 2 alpha delta theta. And we know omega naught is 0. So if I'm solving for alpha so that I can plug in up here, I'm going to have omega squared over 2 delta theta, which I will then plug in here. So, onward and upward, we have r cross f equal to mr squared omega squared over 2 delta theta. And again, what we really want is this final velocity, final angular velocity. So let's solve for that. So to get everything on the other side, that's going to be 2 theta r cross, I just drew a theta again, silly, r cross f, that's not an x, divided by, scroll, divided by mr squared, and then that's equal to omega squared, but I have to square root that, so let's do a square root here, and that should be equal to omega. Now notice that here this r and this r are separate. This little r, that's where the torque applies, and that's the 0.002 millimeters. And this big R is the R of the ring, which was 5 centimeters. I said 0.002 millimeters, 0.002 meters. 2 millimeters, 5 centimeters. They're different, I can't cancel them. And so I've drawn them as a little r and a big R to tell them apart. But I should have all of these values, so I can now plug them in. That's 2 times the theta, which we knew in radians was 150 radians. And I'm keeping everything in angular quantities right now, so I'll cancel later. The radius of the small r was 2 millimeters, or 0.002 meters. The force was 5 newtons. That's top. Bottom, we have an m of the whole ring was 30 grams, or 0.3 kilograms. And the r for the ring was 5 centimeters, or 0.05 meters. So 0.05 meters, and I'm going to square that. And then everything gets square rooted. Whew. Lots in this problem. Let's see if my calculator can chunk all of this. That's 300 times 0.002 times 5 divided by 0.3 divided by 0.05 divided by 0.05. And then I have to square root that. Okay, I'm getting like this, 63. 63, and that should be 2 sig figs everywhere. These were actually 0.0s, so they have 2 sig figs. 2 sig figs, okay. And the 2 is exact, because it actually came from an equation. It was not a measured value, so that's 63. And what's left should be radians per second, because everything was in meters and kilograms and newtons. But that's not what they wanted. They wanted it in revolutions per minute. So I'm actually going to have to do a stoichiometry here. So get rid of radians, let's get revolutions, and get rid of seconds by putting them on top because they're on bottom, and getting minutes. 1 minute is 60 seconds. 1 revolution is 2 pi radians. So 63 times 60 divided by 2 pi. And my calculator is telling me that that is a lot. 604 RPMs. Which, if I'm rounding, this is 2 sig figs, so this is technically 600 RPMs. 600 seems like a big number, but remember, this is in a minute. So if you divide that by 60, it's about 10 revolutions per second, which is still fast. Okay, so again, a lot in that problem to unpack, and it doesn't necessarily look like a rolling problem, but if you wanted to picture this as a rolling problem, you could, because essentially the string attaches at one point like that, and it's almost as if the thing were unrolling. The way you typically handle a gyroscope is you wrap the string like I showed you there. Well, let's give myself some room here. but you hold it up. So here's the axle, and you put the string off to this side, and you just let it fall, and it unwinds as it falls, and that's what causes the acceleration. And in that sense, if you were to just tilt and imagine that you're looking at it from the side, and but the ground is like this way, it's falling, well, doesn't that look like something that's rolling? So that's the similarity between this and rolling motion. Okay, here we go. Wheel rolls without slipping. What velocity vector should we draw for point P? Well, if the object is moving this way, then the wheel is rotating this way. So if I'm following the edge of the wheel, as I get to this point, the tangential velocity at this point would be like this. So it looks like A is the only correct answer, except that that's a tangential velocity. So at point P, there's a tangent velocity, this is v tan, that's going straight up. But the whole wheel has this velocity to the right. So that point actually has two velocity vectors. It has a tangential vector added to a radial vector, and so it should go in this direction. So we're actually going to choose not A, but C. And that's a tricky one to think about, but that is correct. So keep that one in mind. All right. Last one. Two bikes, same mass, and looks like what they differ in is how heavy the wheels are. One of the bikes uses a lighter frame with heavier wheels, and one of the bikes has a heavier frame with lighter wheels, and we want to calculate their kinetic energy. So let's draw one bike, and we'll just use the same formula for both. So here's a bike, like so. And it's traveling forward, like this. And it says to model the bikes as hoops because the spokes are very light. Most of the mass of the bike is on the edge. Or most of the mass of the wheel is on the edge. So we need some kinetic energy equations. Well, the frame of the bike is not rotating. So the kinetic energy of the frame is just 1/2 mv squared if it's traveling at speed v. The wheels of the bike are doing both. The wheels are moving forward with speed v, but they also are rotating at angular speed omega. So this is the frame. This is the kinetic energy of the frame. Pretend that I just drew an F. And then for the wheels, their kinetic energy will be also a linear, 1/2 mv squared, plus their angular kinetic, which is 1/2 I omega squared, and that is the kinetic energy of a wheel. We'll just say that's an individual wheel. So we're going to need this, and I'm going to go ahead and make this omega and turn it into terms of v. So if you remember, a linear velocity can be changed to an angular velocity with this equation. So I will replace that, and for the I, if they're a thin hoop, the I of a hoop should be mr squared. So we'll have the 1/2 mv squared, the linear velocity of the wheel, plus the 1/2, and then we have the I, which is this. So we have 1/2 mr squared of the wheel times the omega. Well, the omega, if I divide by r, should just be v over r. So that's going to be v over the radius of the wheel, which I have to square. And notice when I square it, the radius cancels. So that's a 1/2 mv squared plus, this is a 1/2 m, r's cancel, it's just a 1/2 mv squared. So really when I add it together, it's just mv squared, a 1/2 plus a 1/2. So let's put that back up into here. So the kinetic energy of the wheel is a 1/2 oh, excuse me, I'm not plugging that back in there, that's my bad. I'd already plugged it into there, essentially. So that's the final answer. The kinetic energy of a wheel is going to equal the mass of the wheel, times the v squared. So really, if I'm looking at the bike, there are two wheels, and there's a frame. The kinetic energy of the frame was 1/2 times the mass of the frame times the velocity squared, plus each wheel is mv squared, but that's the mass of the wheel. So it's going to be two of those wheels. So 2 times the mass of the wheel times the velocity squared. Should be the total kinetic energy of the bike. Well, let's take the two different bikes. This is KE total. The first bike's measurements, and both of the bikes were going the same speed, I believe. They're both going 12. Okay. So the first bike, his frame was 10 kilos, his velocity was 12, which I'm squaring, plus the wheels were each 1 mass, so 2 times 1, and their velocity is 12. The second bike was his frame was 9 times the 12 squared, but each wheel was 1.5, so that's a 3 there total. 2 times 1 would be 3, and that's 12 squared. So we just got to put that in the calculator and see what we get. 0.5 times 144 plus 288. So I'm getting, for the first bike, 936 joules. Let's try it for the second bike. 4.5 times 144 plus 3 times 144. And I'm getting 1080 joules. So to get the first bike, which had lighter wheels, that's right, it had a heavier frame and lighter wheels, but the same total mass, to get it up to 12 meters per second took 936 joules of work. To get the second bike, which had heavier wheels and a lighter frame, up to the same speed took 1,080 joules of work. So it took about 150 more joules of work. So when you're a professional cyclist, if you want to use less energy to get more speed, you pick the bike that has the lighter wheels. You cut mass from the bike from the wheels because that's actually more effective than cutting mass from the bike. Because both of these bikes, if you were to lift them off the ground, they would feel the same just lifting them straight up. But when you try to actually pedal them, this one takes a lot more energy, and you want to save that energy if you're competing. Okay. So hopefully this video was helpful in solving rotational kinetic energy and rolling problems.